So you notice that I've skipped one subsection on similar matrices. This subsection is there for your information, but I'll come now to the last subsection of this section 7, which is about the singular value decomposition and singular values. It's the highlight of linear algebra, and it brings together all concepts, and it is used quite a lot. For instance, in model reduction, numerical stability, control, machine learning, and so on. If you write the eigenvalue eigenvector decomposition of A, you obtain this equation over here. And well, there are some shortcomings with this description because it requires A to be square. Okay, so what is annoying here is the inverse. We don't like to work with inverses. We would like a decomposition with a transpose, but this is only possible when the eigenvectors are orthogonal, and in general they are not. Okay, it might be that in some cases it's even not possible to write something like that, because this is here a diagonal matrix, and in some cases, well, the matrix A cannot be diagonalized. There are not enough eigenvectors. Remember, there should be an eigenvector for each eigenvalue. There is, however, a special case when the matrix is positive definite. Okay, and then you can write something like that. So we have the transpose that we like, and also we have here a matrix that is diagonal and that has positive elements on the diagonal. The downside is, well, is only for certain types of matrices, and this is still here a matrix that is square. Well, the SVD solves all those problems in a perfect way. You obtain this decomposition here. Well, first of all, it is for a matrix that can be rectangular, m rows, n columns. Okay, you have a transpose over here, and you have two matrices U and V that are orthogonal. So this is the price to pay. Instead of one orthogonal matrix, as in this decomposition for positive definite matrices, you need two orthogonal matrices. Okay, so let us look at the dimensions of these orthogonal matrices. Well, A is m times n, U must be m times m. We're talking about orthogonal matrices, so they must be square, and so V must be n times n. Okay, when we take the overall product, we want m rows and n columns, so we need an n over here and an m over here. Since these matrices are orthogonal, they need to be square, and we see immediately that sigma has dimension m times n, so it has the same dimension as A. And we will be looking for a sigma that is diagonal, okay, with positive numbers on the diagonal, and these will be called the singular values. We'll see later what we mean with a diagonal matrix, since the matrix sigma is here rectangular. So remember this abstract view of the four subspaces associated to a matrix A. Remember that a matrix A takes a vector that is in Rn and produces a vector y that is in Rm. So you can symbolize this using this vector over here. We have indeed Rn and we have Rm. Remember that the subspaces of Rn are the row space and the column space. All vectors in the row space are perpendicular to all vectors in the null space, and the subspaces associated to Rm are the column space, the left null space, and all vectors in the column space are also perpendicular to all vectors in the left null space, and we had also that a vector in the row space is mapped into another vector in the column space. The dimension of the row space is R. It's the same dimension as the column space. Okay, and the dimension of the null space is n minus r, and that of the left null space is m minus r. So the question underlying the singular value decomposition is the following one. Is there a basis of the row space must contain r vectors? Well, more in particular, an orthonormal basis of the row space that is mapped onto the column space and produces orthogonal vectors. Okay, so is there an orthonormal row space basis? Okay, so we'll draw it like this. We'll call it v1, v2 up to vr. Okay, so these vectors are orthogonal and they have a length 1, so they can well, function as a orthonormal basis of the row space. So how could you construct such a basis? Well, you start from the row vectors, and using Grimm-Schmidt, okay, you can obtain a basis that is orthonormal. And the question is it possible to obtain such a orthonormal basis of row space that is mapped onto vectors that are perpendicular in the column space? Okay, so that are orthogonal in the column space. So they are perpendicular, but they are not necessarily of length 1. So we'll write them like sigma 1 u1, where u1 will be a vector of length n, sigma 2 u2 up to sigma r ur. Okay, so all these vectors are orthogonal, and as you can see, they don't have length 1 because you have these coefficients here, sigma 1, sigma 2 up to sigma r. So this question is at the basis of the SVD, singular value decomposition, and the answer will be yes. So we'll construct the decomposition before we kind of learn how to compute it. So if you take an orthonormal basis of a row space, and you can construct that using Grimm-Schmidt, well, in general, there is no reason why its image should produce orthogonal vectors. Okay, so we're looking for that special orthonormal basis of row space that is mapped into an orthogonal basis of column space, and we'll make the assumption that it is possible, and we'll construct the decomposition, the singular value decomposition as such, and we'll see later that it is indeed possible to compute it. Okay, so the v1 to vr vectors, they form an orthonormal basis for row space, and I've introduced them in the previous slide, and we make the assumption that their image is a vector in column space, and that all those vectors here, u1 up to ur, they are orthogonal. Okay, they are not necessarily of length 1. Okay, they have potentially different lengths, so we can write them as I've done in the previous slide, sigma 1 u1, sigma 2 u2 up to sigma r ur. So these vectors are all orthogonal, and we assume here that u1 up to ur, they also have a length 1, and we adjust the lengths by these coefficients sigma 1 to sigma 2. This is what we had written in the previous slide, but you can rewrite this as the product of two matrices. In the first matrix you put the vectors u1 to ur, and the next matrix is a diagonal matrix in which you put on the diagonal these coefficients that you have over here. Okay, and using this column interpretation of the product of this matrix by this one, we see that this indeed is the same thing as what is written over here. Okay, so the first column over here is a linear combination of the columns using this first column, so you will indeed select sigma 1 u1. Okay, this is at the heart of the SVD, but we need more. Okay, so we know that A is m times n, so this as r column, so this matrix is n times r, the product is m times r. So here we'll have something which is m times r, and this is a diagonal matrix r times r, so indeed this is consistent, and this is m times r. But we were talking about a matrix that was orthogonal and square, therefore, so we need a matrix that is in Rn times n. Okay, so we need nr more v's. Okay, and we'll find them in the null space of A. This is the null space, and it is orthogonal to the row space. Okay, it's even the orthogonal complement of the row space. So here we have a matrix U, and we would like it to be in R m times m. So we need a few columns here. Okay, we need actually m minus r more u's. Okay, and we'll find them in the left null space. Okay, remember that the left null space is the orthogonal complement of the column space. Okay, so this is kind of the, well, a reduced singular value decomposition is at the heart of the SVD, but we need to extend it to obtain this full SVD. Well, let us take an orthonormal basis of null space, and we've seen that we can obtain that using Grimm-Schmidt, right? An orthonormal basis will have n minus r vectors, and these vectors are orthogonal to the first r vectors. That's simply because, well, the null space is the orthogonal complement of the row space. Okay, so these n minus r vectors, we stack them over here just next to the first r vectors that are coming from the row space. Okay, so in the matrix U we needed m minus r vectors, and we'll take them from the left null space, and we'll take an orthonormal basis of the left null space. These vectors will automatically be orthogonal to the r first vectors, since the left null space is perpendicular to the column space. So we've added m minus r vectors over here and n minus r vectors over here. It's kind of, well, easy to see that you need to adapt the dimensions of sigma over here. So remember that AV1 is sigma 1 u1, but now we have added here m minus r columns, so you need to add some zeros below here. Okay, and you need to add a matrix of zeros of dimension m minus r so that everything stays compatible and with the width of this original matrix over here. Okay, and you can see that if you add zeros over here, well, this relation keeps on being true. Okay, so we have adapted the matrix sigma to account for the m minus r columns that are added over here. Of course, we have added also n minus r columns over here, and we know that these vectors that we've added are such that ax is equal to 0. Okay, so we need to add here a matrix that contains zeros. It must have n minus r columns, right? And it must have, well, since we have here m columns, well, we need to have m rows over here to be compatible. Okay, you see that you have here r and there m minus r, so this whole matrix, if you consider it to be one matrix, as indeed m rows of zeros, and each row contains n minus r elements. Okay, so this leads to the full singular value decomposition, and you see that the matrix sigma has, well, n columns and m rows, so it has the same dimensions as A, as we had seen previously. Okay, so this is the decomposition that we had obtained in the previous slide, right? With here the matrix V, the matrix U, and sigma. And by construction, V and U are orthogonal matrices. So what we can do in this relation, we can post multiply by V transpose, and then you obtain this equation over here. Okay, and V times V transpose is indeed the identity matrix. So you can write A as this relation over here, and this is the, well, singular value decomposition. Okay, so what we can do is write U in terms of its columns, V transpose in function of its rows, and it will be, of course, the columns of V, and it's a V over here, it's not very clear, so we'll write V transpose as a function of its rows, and it will be, of course, the columns of the original matrix V that have been transposed. Okay, so it's clearly in terms of the rows over here. So if we take this product over here, we know that if you do the multiplication of two matrices, well, you obtain and if you take the column interpretation, well, you obtain for each column a linear combination of the columns of U. For instance, if you take the first column, well, you'll take sigma 1 times U1 and then 0 times all the other columns. So this is why you obtain this over here. You can go up to sigma r UR, and then for the n minus r remaining columns where all coefficients are 0, so you obtain here columns, n minus r columns full of zeros. Okay, so this is U times sigma, and now we need to multiply by V transpose, and we do a kind of block multiplication. We have U sigma divided in terms of columns, V transpose in terms of the rows. So we know that if we do this by block, we do first column times first row plus second column times second row, etc., and we obtain this decomposition of the matrix A. So this decomposition over here is equivalent to this decomposition over here. And you see that each time, in each term, you have a rank 1 matrix. You remember that a rank 1 matrix can always be written as UV transpose, so a column vector times a row vector. So we have decomposed here A in a sum of R, where R is the rank of the matrix, in a sum of R rank 1 matrices. Well, this is what we had obtained in the previous whiteboard explanation. We have decomposed A as U sigma V transpose. You can rewrite it as a sum of matrices of a rank 1, and in the sum you have R terms where R is the rank. U and V are orthogonal. Sigma has the same dimension as A and is diagonal. And you know now what we mean by diagonal. So look at this structure of sigma, and on the diagonal you find the sigma I from 1 to R. I goes from 1 to R, and these are called the singular values. They can be chosen as positive numbers. Okay, and in this decomposition we'll make the assumption, and this can be done without loss of generality, that all sigmas are ordered in descending order. So sigma 1 is larger than sigma 2, etc. Okay, sometimes we use this reduced singular value decomposition that you have over here, and so this means that we are forgetting the m minus r vectors coming from the left null space in U, and we forget n minus r vectors coming from the null space. Of course, both decomposition lead to the same rank 1 sum decomposition. Okay, because what is added over here will not influence the sum, as well the vectors that are added are linked to elements that are 0 in this sigma matrix. So this is the decomposition that we had obtained, and the singular value decomposition. Well, if somehow we can compute this decomposition, this gives us another way of obtaining, well, basis, orthonormal basis for the 4 subspaces of A. Okay, because by construction we know that the first R columns of V, okay, correspond to the row space, and the first R columns of U correspond to the column space. Okay, and the n minus r last columns of V correspond to the null space. Okay, last n r columns of V, and the last m minus r columns of U correspond to the left null space. So if you have this singular value decomposition, then it's very easy to find this orthonormal basis. So we have kind of constructed the decomposition of A is equal to U sigma V transpose from the definitions of the 4 subspaces of this matrix A. But we would like, of course, to find another way to compute this decomposition. Okay, well, this is easily seen by computing A transpose A. Okay, so if you compute A transpose A, you have A over here, you have A transpose. You remember that, of course, A B transpose is B transpose A transpose, so you can rewrite this to this thing over here, and this is indeed an identity matrix. Okay, so if you compute A transpose A and you do an eigenvalue eigenvector decomposition, then the sigmas are the positive square roots of the eigenvalues of A transpose A. Okay, remember that this looks like something like we had written it a little bit differently. We had written it Q lambda Q transpose. Okay, so in here you have the eigenvectors, or maybe in here in V you have the eigenvectors of A transpose A, and in sigma you will have the square roots of the eigenvalues of A transpose A. And since A transpose A is non-negative, well, these eigenvalues will be positive or 0, so you can take that square root. of course, what you can do is compute A transpose. In A transpose A, U had disappeared, and if you compute A transpose, well, it's V that will disappear. Okay, and you obtain kind of the same kind of decomposition, but now you can obtain the eigenvectors of A transpose, and you put them in U. And okay, the singular values will be again the square roots of the eigenvalues of A transpose. So this gives you a way of computing this singular value decomposition. Well, remember that when you normalize vectors in general, you generally have two possibilities, because if U, for instance, is a unit vector, minus U is also a unit vector. Okay, so it's important to remove this degree of freedom, and we remember the equations that we have written at the beginning of this subsection. Remember that the VI are, well, vectors that are in the orthonormal basis of a row space, and they are mapped on vectors in column space that are, well, orthogonal, but their length has changed. It's not necessarily anymore a unit vector, so we write it as a unit vector times a scalar here that is positive. Okay, so if we normalize, this equation should hold for I equals 1 to R. Well, there is a geometrical interpretation to A is equal to U sigma V transpose. So if you apply A, the first thing that you apply is of course V transpose, and then you take the result, you apply sigma, and then you take the result and you apply U. So this is why you have the order over here. Remember that V and U are orthogonal matrices, so they are such that when you take an image of a vector, well, the length is preserved, and if you would take the image of two vectors, the angle between the vectors are preserved. Okay, remember that we have seen a few examples of that. For instance, they are rotation, reflection matrices, etc. So you can see the matrix A as rotation, for instance. Okay, then sigma, of course, it's just elements on the diagonal, so you'll do at some stages you'll well, extend the length, or you reduce the length, and then the U matrix might be, for instance, another rotation matrix, but it might be a reflection as well. Okay, so U and V are rotation or reflection matrices, and sigma stretches the vectors. It makes them longer or shorter, and this will be illustrated in an example later on. So we'll do an example of the computation of an SVD. There is a second example, but I will skip it. I will leave it as an exercise for you. So I start with this matrix over here, and we want to write U sigma V transpose. This is obviously a matrix of rank 2 because the columns are independent, so well, we'll have two terms in the rank 1 decomposition. So the first thing that we do is compute A transpose A. Okay, this is this matrix. I'll leave you the calculation. You can see that the eigenvalues are 8 and 2. The trace is indeed 10, and the determinant is indeed 16. So this is correct. So we know that A minus lambda 1 I times V1 is equal to 0 will be the solutions that will allow you to compute the eigenvectors. Okay, so this will give us minus 3, 3, 3 minus 3 times V1 is equal to 0, and indeed this will give us 1, 1. Okay, and of course we'll divide by square root of 2 in order to have unit length eigenvectors. Okay, you can do something similar for the other eigenvalue. Instead of -3 over here on the diagonal, you have +3, so you'll obtain v2. Well, it's written over here. Okay, so v2 is written over here. Okay, so we know what to stack in the matrix V. We know what the singular values are. We simply need to take the square roots of lambda 1 and lambda 2. This leads to sigma 1 and sigma 2, and the u's we can simply find by writing that a v I, okay, I is here 1 or 2, is sigma I ui. And if we do that for these two vectors, well, AV1 is this vector over here, AV2 is this vector over here, and it should be sigma 1 times a unit vector. Sigma 1 is 2 square root of 2, and sigma 2 is square root of 2. So obviously we find u1 and u2, okay, and we can write the singular value decomposition of the matrix A. So if you take the vectors v1, v2, you can obtain the matrix V, and if you take its transpose, you obtain this matrix over here. So this is indeed here v1 transpose, and this is v2 transpose. And if you take u1, u2, you put them in the matrix U. This leads us in this particular case to an identity matrix, and here you have sigma 1 and sigma 2. Okay, so you can ask the question, if you had computed A transpose, in this case it leads us, well, to this diagonal matrix. You see that the eigenvalues are the same, therefore also the, well, singular values and the square roots of the eigenvalues are the same, and you can easily see that the, well, eigenvectors will be 1, 0 for the first eigenvalue, for instance. But the question is, why not choose -1, 0, which would also be a vector of length 1? Okay, remember that if v is an eigenvector, then kv is also an eigenvector. Okay, so why not choose this one? Simply because we have to impose this relation over here. Okay, and then we see that this case is not possible. Okay, so here we have our decomposition u sigma v transpose for this particular 2 by 2 matrix. So there was also another interpretation of the decomposition A is equal to u sigma v transpose. The idea was that you could write it as a sum of terms like that. In general, you have a number of terms that corresponds to the rank of the matrix, and indeed here the rank is 2, so we have 2 terms, and it's each time the singular value times the u and the associated vector in the U matrix times the associated vector in the V matrix transpose. Okay, so this is a rank 1 matrix. This is also a rank 1 matrix. If you do the calculation for this particular matrix, this is the decomposition that we obtain in some of rank 1 matrices, and we'll see later on how this can be useful. There is something that we have not done yet, and I would like to do now, is look at this, well, geometrical interpretation of this decomposition of the matrix A. So here we have rewritten the singular value decomposition of the matrix A, right? So it's u sigma v transpose, and remember that these matrices u over here and v over here it's V transpose. Well, they are orthogonal matrices, so they are related to operations such as rotation and reflection. We will see here that V transpose is a rotation matrix. In general, a rotation matrix can be written like this, and in this particular case you can see that, well, in order to have a positive cosine and negative sine, you need a negative angle here, and it corresponds to minus 45 degrees. Okay, so the matrix V transpose corresponds to a matrix that is a rotation by minus 45 degrees. Okay, so the sigma matrix will of course be corresponding to a stretching. Okay, and obviously as the matrix U is the identity matrix, will obtain, okay, the result of the previous two operations as they are. So you can see A as taking the vector that you're applying on A, making a rotation by minus 45 degrees, then stretch and then keep as is. Okay, so we'll take two vectors that are a bit special, so we have the same representation as we have in the slides. We'll take the vector v1 here and v2. There are several ways to compute its image or their image. You simply take a times v1 or a times v2, you compute, and you'll end up with these vectors over here. Or you remember that av1 is sigma 1 u1 and that av2 is sigma 2 u2. Of course you obtain the same result. Okay, so the vectors v1 here and v2 are given over here, and you can clearly see that they have length 1, okay, and that they are perpendicular. It's normal because V is an, well, orthonormal or orthogonal matrix, and the vectors are orthonormal. So let's take v1 and apply the matrix A. So you should end up with a vector that is over here. Okay, and let's do this in the way that is suggested by the singular value decomposition. Well, we have to do a rotation by minus 45 degrees. Okay, this is what you see over here. You end up in 1 0, and then you have to do the stretching operation, and indeed you end up over here. And well, the last matrix U keeps you on the same spot. Okay, so we see that indeed this geometrical interpretation is correct, and we can do the same thing for the vector 2. This brings me in the vector 0 1, rotation by minus 45 degree, and then this stretching operation, okay, with this coefficient over here, and this leads me to the vector 0 square root of 2, and this is indeed the result that we should obtain. So the geometrical interpretation of the SVD is that it is decomposed in a number of operations: rotation, reflection, stretch, and then rotation or reflection again. So we will continue with section 8, applications. Most of the information here is for your information, so I will talk a little bit about compression, image compression. Not that I want you to do image compression, but the same ideas hold for model reduction. And as a control engineer, well, at some stage you might have to do model reduction. We'll talk a little bit about the performance of multivariable systems, about matrix condition numbers, and I'll talk a little bit about principal component analysis and Matlab commands. So, image compression. So the SVD comes into the picture each time you want to approximate a matrix by another matrix. Okay, and this is, for instance, the case for image compression, and I'm using this example to show you how good this SVD is, not to actually tell you to do image compression this way, because there are algorithms that are much better than the SVD to do image compression, but you can see things visually. But for instance, approximation of a matrix by another matrix is important when you do model reduction. As I've said, as a control engineer, at some stage you might want to replace a model by a simpler model, and behind that somewhere is the SVD. So remember that we have decomposed A as U sigma V transpose, okay, and that you could, well, rewrite A as a number of rank 1 columns, and there are exactly R terms over here where R is equal to the rank of the matrix A. Okay, so U1 here is the first column of the matrix U, and V1 transpose, well, V1 is the first column of the matrix V, and sigma one here, well, it's the first singular value, it's the one associated to U1 and V1, and you have R terms like that. Remember that without loss of generality, we have assumed that sigma 1 is larger than sigma 2, etc. Okay, so how can we approximate the matrix A by another matrix? By simply taking fewer terms in this sum. So we can, for instance, start crossing out from this side over here, because the influence is the smallest as the singular values are smaller. So here we have A is a rank R matrix, and if you cross out a few terms, you end up with a matrix that has the same dimensions but has rank R bar, and R bar is the number of terms that you take into this sum, and it's defined over here. Okay, so we will see visually what will happen if we take a matrix. This matrix will have rank 200, it will be an image, and we'll start compressing it. So this is the code that we'll be using to do the image compression and to illustrate the SVD. So we load the original image and we obtain, well, the matrix that is important. It's the X matrix. It will be 200 times 320, and the rank of the matrix will be 200. Okay, so there is also a color map associated, but well, don't bother about that one. What is important is X over here. So what we do is first picture with the original clown picture, and then what we do is use the Matlab SVD command for, well, singular value decomposition. There are different modes that you can use. I suggest you have a look at the help of Matlab for that, and you obtain U, sigma, and V. Okay, so the original matrix has rank 20. So what you can do is maybe obtain a rank 5 matrix. Okay, so A can be decomposed as 200 terms of the type sigma 1 U1 V1 transpose plus sigma 2 up to sigma 200 U200 V200 transpose. Okay, so if we take a rank 5 matrix, well, we take 5 terms in the sum. Okay, so how can we do this? Well, we have to isolate the 5 first columns of U, the 5 first columns of V. This is done over here, and we need to create a square matrix of dimension R times R, 5 times 5 here, in which we put the singular values on the diagonal, and then we can reconstruct by taking the new U, V, and S, the new image. Okay? It's U new times S new times V new transpose. And then we can have a look at a picture of the reduced clown, the clown with image compression. You can also compute a compression index. Okay, so originally you needed NR times NC elements to store. That's the 200 times 320. And in the new image, well, you need for this one here NR times R, for this one R times NC, at least for the transpose, and on the diagonal you need R terms. So this is the new size, and if you, well, use this expression here, you kind of obtain a compression factor. Well, what we'll do now is have a look at the image, the original one, and then start comparing with the rank R pictures. So this is the image that will compress. As I said, the original image has size 200 by 320, and if we take an R rank picture, well, you need 200 times R plus R plus R times 320. Okay, so this might lead to some compression, but in the end, if the rank of the matrix becomes high, at some stage you'll see that you need more elements to store everything using this approach. Okay, one thing that should be obvious, the SVD decomposition compresses with a loss of information. That will be pretty obvious when you see the next picture. And again, I'm not suggesting that you should do compression using this method. This is a way of illustrating the SVD visually. So let us start. So this is on the left the original clown, as you can observe, and right next to it, it's very obvious, the rank 1 approximation. Okay, so you will see that the SVD is very good at capturing the important features, but of course you need more than a rank 1 matrix. So let us start, increase the rank of the matrix. This is 2, 3, 4, 5, 6, 7, and 8, and I think that by now you could, if you show this picture to someone, well, tell that it is indeed a clown. So you have captured the most important features of this face of this clown. And if we continue, we can see that here 20 and 25, well, we have already a very good approximation of the picture with a rank that is pretty low in comparison with the rank of the original matrix. Okay, or if you continue, of course, the results become better and better. At some stage, you see that, well, to store the data, you need more place than with the original matrix. And this is the last time that we did. Okay, so what we see over here is that you can approximate a complex matrix by one that is much simpler. Okay, and this has applications, as I said, in model reduction. Well, a next application is the singular value response, and the singular value response extends the Bode magnitude response to multiple input, multiple output systems, and they are useful in robustness analysis. Okay, and in the singular case, CISO case, single input, single output, well, this singular value response is identical. It corresponds to the Bode magnitude response. So let us consider, for simplicity, a MIMO system with only 2 inputs and 2 outputs. You can write it as, well, y1s, y2s, Okay, that's a vector, and we'll call it y of s over here, gs times, and then you have u of s, and we'll write it as u1s, u2s. Okay, so what you could do if you want to consider this system, this MIMO system in the frequency domain, is to of course work with Bode diagrams. So you look at this transfer function, and this is a transfer matrix, and this is a transfer function. It goes from u1 to y1. This one goes to u2, from u2, sorry, to y1. This one u2 to y2, and this one u2 to y1. So you could look at 4 Bode diagrams. So what they give you is the steady state gain and also phase information at a given frequency. Okay, of course, if this extends to lots of inputs and outputs, you'll have lots of Bode diagrams to consider. Okay, so what you could do is look at the gain here, and what you have to understand is that the gain, well, when it's multivariable, depends on the direction that you're looking, and the direction that you're looking, well, depends on the type of vector that you have at the input over here. So you could look at a given frequency at the gain that you have, and we'll express it like this. So how high can this gain? And it will, of course, it's not unique, it will depend on the type of vector that you have here. How high or how low can this gain get at a given frequency? And again, we'll assume that we are in a steady state. And what you can show is that this has an upper bound, which is sigma max. So this is the largest singular value of the matrix that you consider at the given frequency, and the lower bound is sigma min, the smallest singular value of that same matrix that you consider at s is equal to j omega. And this leads to the singular value response. What you'll get is something similar to a Bode diagram with 2 curves on it. Well, the highest gain that you have and the smallest gain that you have at that particular frequency. So let us take an example of that, and for that we look at this part. The remaining part has to do with some stuff that I have skipped and I left for your information. So I've got here my 2x2 system, and what I can do is simply do the Bode diagram. I'll obtain 4 Bode diagrams using the command Bode, or using the command sigma here, I will obtain my singular value plot. Okay, so this is what we obtain. So indeed we obtain 4 Bode diagrams. Okay, each time from input 1 to output 1, input 1 to output 2, and then the same thing starting from input 2. So you look at, well, Bode diagrams in a certain direction, because here you kind of assume in this Bode diagram that E, the second input, is equal to 0. Okay, so you have only information in certain directions, okay, in directions where one of the inputs is 0. Well, another aspect is that when the number of inputs and or outputs increases, the number of Bode diagrams, of course, increases as well, and so this might become untractable. So this is not a very practical solution, so it might be a better idea to have a look at this singular value plot. And as I've said, well, you have a plot over frequencies, and you have an under bound sigma min and upper bound on the gain at a given frequency. Okay, so the x-axis is frequency again, and of course you're assuming that you're in steady state. So let's look at a given frequency over here. Let's assume that we take the frequency omega is 1 radian per second. Well, then you can say that the minimum gain that you have in the case of a multivariable system, the gain is not unique. It depends on your input, okay, that is composed here of u1 and u2. Well, the minimum gain that you have is, well, minus 10 dB over here, and the maximum gain at this frequency of 1 radian per second is approximately, well, let's say 12 dB for another input vector in another direction. Okay, so at any frequency the gain of this multivariable system is in between lower bound and in upper bound. Okay, and so there is also another important parameter, which is the infinity gain of the system. This is the maximum gain that you have overall. Okay, so it's the maximum of the upper bound over frequency. Well, as I've said, this has applications in robustness analysis, but also robust control. We have spent a lot of time on the system of equations ax is equal to b. Okay, well, I've talked about numerics a little bit and told you that in some cases you can expect numerical problems, and this is related to what is called the condition number of the matrix A. Okay, let us assume that the real system is ax is equal to b, and associated is the actual solution x. Okay, but that your system that you're solving, okay, is a little bit different in the sense here that b is changed to b plus delta b. Okay, this could be because your computer makes a round off error, okay, or there is an error on the original measurements of b. Okay, so the system that you're now solving is ax is equal to b plus delta b. Okay, and the solution will now be x plus delta x. Okay, what I would like, if the system of equations is well posed, is that if delta b is small over here, I would like a small relative error on x. Okay, and this is the relative error. Okay, so I would like an equation of the type where the relative error of x is bounded by the relative error on b times something, and this something is the condition number, and this condition number I want it to be as small as possible. This condition number can be computed, okay, as this quantity here where you have a certain norm. This is something that we have skipped, but in the case of the 2 norm, okay, so we'll put this between parentheses because we have not seen it, but in the case of the 2 norm, you can compute the condition number of A as sigma max of A divided by sigma min of A. So you divide the maximum singular value of A by the minimum singular value of A, and this gives you the condition number, and it should be as small as possible, and this gives you a way to see if your matrix will be subject to numerical problems in the solution of the system X is equal to B. So the next thing I want to talk about is about the principal component analysis, and this is a technique which hinges on linear algebra and more in particular on the SVD. It transforms a number of possibly correlated variables into a smaller number of variables that are called the principal components. I won't go into the details of the computation and things like that because it's quite heavy, but I just want to say that it's based on the SVD, and I want to give you the general ideas using an example. So we start with data, and this data is organized in a matrix. Okay, so we say that there will be m rows. In our case, m is 150, and this corresponds to the number of observations that you have, or the number of samples, and each sample corresponds to a number of variables, and these correspond to the columns, and in our case n will be equal to 4. Okay, this is not very important, but we'll make the assumption that every variable has a zero mean, and if this is not the case, well, you should subtract the column mean from each column. So the data set that we'll be using is called, well, Fisher's iris data set. Well, it's a data set of 150 measurements that have been made on 3 types of iris flowers: Iris setosa, Iris versicolor, and Iris virginica. Okay, so it's a set that was measured in 1936, and it's often used in classification problems. If you want more information, you can have a look at this link on Wikipedia. So the data from the iris flower data can be loaded into Matlab using load Fisher iris. Okay, and what you obtain is indeed a set with 150 samples, and each sample has, well, 4 variables: sepal length and sepal width, petal length and petal width. Okay, so you also have information about the species, which type of iris is it, but this will never be used in principal component analysis. Okay, the idea of principal component analysis is to kind of remove the redundant information. As you can guess, of course, sepal length and sepal width are kind of correlated, and so are petal length and petal width. Okay, so if you don't have PCA, what would you do? Well, you would start to look at graphs where you put one variable on the x-axis and the other variable or another variable on the y-axis. And this is exactly what we will do before we explain, at least intuitively, what we'll do with principal component analysis. So this is what we have done. If we plot one variable against another, well, we have in total 6 plots. Of course, if the number of variables increases, this kind of method of course becomes untractable, because the number of plots that you have to consider will blow up. Okay, so what can you see in these plots? Well, you can see that there is indeed correlation. Okay, you see that the petal length and the petal width is very strongly correlated. Okay, you see it for other variables as well, and you kind of see that you've got the best separation when you consider petal information and sepal information in general. So this is the technique here that we have just applied. We use what is called scatter plots. We plot one variable against another and we analyze things. Of course, if there are n variables, well, the number of scatter plots will become very high, and so this is the number of combinations of 2 in n, and clearly for large data set with large numbers of variables, this is not feasible. Well, PCA principal component analysis generalizes this idea. In our example, we have 4-dimensional data for 150 flowers, so we can imagine plotting the 150 coordinates in a 4-dimensional space. So we would have a point for every flower in this 4-dimensional space. If there would be correlation, it could be observed in this 4-dimensional space. Of course, we cannot visualize such a 4-dimensional space, so we are not able to see the clustering directly. But this is the idea that is behind. Let's first try to imagine things in 4 dimensions and then maybe try to be a little bit smart. Well, principal component analysis will allow us to be smart. So what we do is use a new set of orthogonal coordinate axes called the principal components in our n-dimensional space. Okay, and the idea is to explain as much as possible of the variance. So let's assume that we would be in a 3-dimensional space and that the data points look like a rugby ball. Well, what we would use as a set of orthogonal coordinate axes would be the principal components associated with this ellipsoid. Okay, well, you can do this in any n-dimensional space. Okay, then when you rewrite your data in terms of this new coordinate axis, in lots of cases we can account for the vast majority of the variation in the data using only the 2 first coordinates, and we forget about coordinates 3 to n. This means that we can represent things again in a 2-dimensional space, okay, in a 2-dimensional plot. So this is how we do this in Matlab. So we load the data and then we use the PCA command. So this is the original measurements. This is this matrix that has 150 times 4 elements. Okay, and in this example over here we assume that we want to retain the 2 first principal components. Remember that we consider these points in a 4-dimensional space, and then we kind of find the basis that best represents the data, in the sense that the first axis represents most of the variation, then the variation that is left is best represented in the second axis, and so on. Okay, so this is each principal component. So this is how much of the variance in the data that is explained by each principal component, and this is the coordinates of each data point in this new basis of principal components. Okay, so the first thing that we do is have a look at the percentage of the variance that is explained by each principal component, and here we have chosen 2 principal components. So what we can do is make a scatter plot of the first and second principal components, and then plot the new coordinates of each flower in this new basis. Okay, so if we look at the first figure, we see that more than 90%, so 92% of the variance is explained by looking in the first direction. Okay, by taking simply the first principal component. You can add maybe 4 or 5% by adding the second principal component. Okay, and you can see that there is a lot of redundancy, because when you look at the third and fourth component, it does not explain a substantial part of the data. So these components 3 and 4 can be forgotten, and in this case you could even say, I will forget about the second component because it explains already 92% of the data. Okay, so this is the scatter plot that comes from the principal component analysis. So on the x-axis you have the first principal component, on the y-axis the second principal components, and here we have, well, shown every data point, okay, with the type of iris that is associated. I want to stress the fact that we did not use, of course, this type of iris information to do the principal component analysis. And without a surprise, well, the first principal component is more or less in the direction of petal width, and the and length is more or less in the direction of petal information, let's say, and the second principal component is more or less in the direction of sepal information. So if you would consider the third principal component, you would have an axis sticking out in this direction, but there would be hardly any variation along this axis. Okay, so in this high dimensional space, well, everything is on a plane. This is why you can explain things by looking at two principal components, and this is often used for classification. So you bring everything in this first, second principal component scatter plot, and then you can start to do the classification. So now if you have a new flower, okay, so you apply the same transformation and you bring this new point into this principal component scatter plot, and you can kind of then decide what type of flower is it, setosa, versicolor or virginica. So finally, maybe a summary of some Matlab commands. Some have introduced, others not. So, well, determinant, trace, the inverse of a matrix, the transpose is with like this. Then the rank of a matrix, the LU decomposition, the row reduced echelon form, and these two have not introduced, null and ort. Well, this gives you an orthogonal basis for the null space and for the column space respectively. I have not introduced, I think, the command for the QR decomposition. It's important to put the 0 over here so that you have the complete information. This I have introduced, the eigenvalue command. Eigshow is something that you can use, but it has disappeared from the Matlab commands since, well, Matlab 2016. Then Scholl for Cholesky factorization, and this is a factorization R transpose R is equal to A, and then you have the singular value decomposition. Well, I will show you with a small example that you can have problems with the eig command that allows you to compute the eigenvalues and the eigenvectors. I've taken here a matrix A with repeated eigenvalues, but you will see that it's not possible to diagonalize the matrix A because there is, well, not an eigenvector for each eigenvalue, but you will see that this command will try to find this diagonal form even if it does not exist. So let's illustrate that. So here's the matrix A that we have considered. It's kind of very easy because it's upper triangular and we have the eigenvalues here on the diagonal. Okay, let's have a look at D. Of course, D is 1, 1, 2, so indeed the eigenvalue 1 is repeated and the eigenvalue 2 is a single. And if I have a look at the matrix V, okay, you can see that Matlab tries to make it into a diagonal form, even if this is not possible. Okay, you can see clearly here that the vector v1 and the v2 are multiples from one another. So beware when you use this command that there might be strange results when the eigenvalues are repeated. So here on top I've skipped everything in the course. The only command that might be interesting is this one over here that gives you the condition number, the 2 norm condition number. It's actually, well, sigma max of A divided by sigma min of A. And remember that this might be something that you could check if you have systems of equation AX is equal to B and you experience, well, numerical problems. It might be that your matrix is almost singular, and you will see this by looking at this condition number that will be probably very high. I have not talked about the pseudo inverse, but remember that in least squares, or if you consider a left inverse, well, you consider this matrix over here. But in some cases, and this is making the assumption here that the columns of A are independent, but if this is not the case, this matrix has no inverse and you cannot speak of this left inverse. Okay, and then you have something that is called the pseudo inverse, and it's also based on the singular value decomposition U sigma V transpose. You can have a look at it. It's in the course and it's there for your information. And I've just talked a little bit about the, well, principal component analysis. This completes this video.